Good morning, good afternoon, everyone. We will wait a few more minutes to get started so that we leave enough time for everyone to join. But thanks already for joining. I see more and more people joining. So yeah, again, good morning and good afternoon, everyone. Nice to see some nice attendance to this webinar. It's a very important and interesting topic. So I'm glad to see so many people joining. I'll give it one more minute and then we'll get started with the introduction and the content that I'm sure everyone is looking forward to. I still see some people joining, but it's 2 minutes past the hour. So in the interest of time, we will get started. Hi everyone, welcome to this webinar. My name is Rajon Bernard. I am a senior researcher at the ICCT International Council on Clean Transportation, one of the co-authors of the study that will be presented today. So thank you very much for attending today's webinar. You might have heard of have had an information that this webinar will be recorded and it will be available on ICCT's YouTube channel in the coming days. Today we're going to talk about our recently published report. So if you haven't seen it, I think the link will be posted in the chat. This report is about the benefits of smart EV charging for power grids in Europe. We have 3 speakers today. First, Julia Hildermeier. She's team lead for e-transportation in the EU program of RAP, the Regulatory Assistance Project. Then we have Marin Dilé, he's project manager at Artelys, and I will also be a speaker today and the moderator. So that's a bit about our speakers. Thanks already to the speakers for taking their time to present the study today. And if you go to the next slide, I'll give a brief look at what we will be covering today. So Julia will start us off with a quick introduction to the project and its context. Then I will dive into the modeling of EV charging demand for 2040. And then Marin will talk about the value of smart charging on the Essonne grid, and Julia will wrap up with the results and some conclusions. And at the end of this, we will have a Q&A session. So throughout the presentations, I encourage you to post your questions in the chat, and the speakers will either answer them in the chat or answer them at the end during the Q&A. The presentation will last around 35 minutes, and that should leave us at least 10 minutes to answer your questions. And that's about it for the context and for the intro and agenda. So I'll turn it over to Julia to start us off.
Thank you, Marie, and welcome everyone. To give a bit of context and background to the study, as I think you all know, the EV market globally, but also in Europe, has been accelerating fast. This is stock pictures for Europe for passenger cars and electric trucks. And it's important to note that despite the recent sales slope on the passenger EV side, the market is recovering, and we're also noting a particularly strong growth on the heavy-duty electric segment. So with all this, next slide, please. The power demand from electric vehicles is growing. And with that growing number of EV demand, it is really essential to smartly integrate all these electric vehicles into our power grids. Optimized or smart charging is really essential to to bring down the costs of this integration and advance the energy transition. In other words, if we don't integrate that demand in a smart way, we risk to slow down the energy transition overall. So what does smart charging mean exactly? Smart charging means that we charge electric vehicles at the best time for the grid, ideally in an automated way, based on price signals that convey when is the best moment to charge. Price signals that convey when electricity and grid use is cheapest, so users can make savings, but we can also make savings on the grids. More precisely, the benefits are delaying or avoiding grid upgrades, reducing system cost overall, and help integrate renewables, which then also stimulates further investment in renewables and eventually reduces GHG emissions. So these benefits are more and more known in the sector, which is good news. But how exactly can we find out how high these benefits are? And how can we measure the potential of grid savings from optimized or smart charging? And that really was our question in this project. Can we quantify the economic benefits of smart charging from a power system perspective? So we defined those benefits as avoided grid costs on the power grid from smart charging. And to answer this question, we took the approach to look into selected regions in four of the largest electric vehicle markets globally and study the benefits from integrating EVs into the local energy system. Next slide. So this is a brief, just sort of picture on the work we did. The study we're presenting today on Europe is part of this global project in which we studied 3 other regions. In India, a highway freight corridor in India, and how it can be electrified in a smart way, benefits of smart and bidirectional charging in a selected province with high EV uptake in China, and optimization potential from charging the projected EV fleet in a selected state in the US, which has high renewables targets. So each of these studies are available on RAP's website, but also stay tuned for a global guide, a short summary that will guide you through the insights and learnings from all of these case studies. So today is about the Europe installment of this global series. And by means of introducing our case study today, next slide, here's how we designed the research. Here's a quick snapshot of our methodology. What we did in each region, in a nutshell, is projecting the number of passenger and trucks that we expect on the roads in a certain year. We then derive the electricity demand from that projected EV fleet and the associated charging infrastructure that is needed to charge it. We then build scenarios from optimizing the charging of these vehicles based on a number of assumptions that we'll go through in much more detail. And we then assess the potential to shift EV consumption, to optimize it. And we estimated the cost that could be saved based on some fine-grained grid modeling that is the focus of today's webinar. So with that quick context and background, I'm handing it over to Marie and then Marin to take us through the case study today.
Yeah, thank you, Julia. So if you go to the next slide, I'll speak mostly about the 3 first steps of the methodologies that Julia highlighted, and first introduce the case study that we did. If you go to the next slide again, we focused the case study on Essonne. It's a department in the south of Paris, as you can see on the map here. We chose Essonne as a case study because it's to be as representative as possible of as many areas in Europe. Because it has a mix of urban, semi-urban, and rural areas, it increases the representability. And we also chose Essonne because there was data available to do some fine modeling on the grid network. One thing to keep in mind, since we chose Essonne as a case study, is and keep this in mind for the results later on. France is already quite an electrified country with a future-proof grid, it means that the results that we are presenting are quite conservative, and some higher benefits of smart charging can be expected in other European countries. If you go to the next slide, I will quickly talk about the fleet and charging modeling, so the 2-3 first steps that Julia went through. At ICCT, we developed several models to forecast EV uptake and charging infrastructure needs for both light and heavy-duty vehicles. Our EV uptake model is called ICCT Roadmap Model, and charging models are called EV Charge and HDV Charge. And we use these 3 models for this project. As you can see on the flowcharts, on the right step is the different steps, and on the left side, it's the inputs for the different modeling steps. The first step is to forecast the number of EVs on the road by 2040. And for this, we used ICCT roadmap model with adopted policies. So we looked at all the policies that are already implemented, and we fed them into the model to have an assessment of the number of light and heavy-duty electric vehicles on the road in 2040 in this French region. And then after estimating the number of EVs, we allocated these EVs to charging needs group. A charging need group basically means that we regrouped EVs with the same characteristics. So for example, an EV driver with access to home and workplace charging is in one group, an EV driver with access to only home and no workplace charging is another group, etc. So we regrouped them into different charging needs groups, and that's based on assumption related to access to home and workplace charging, related to the share of EVs used to commute, etc. After that, the third step is to calculate the energy needs for all of those EVs and split this energy by charging setting. And for the energy part, we look at the annual mileage and efficiency of the EVs. And for the charging setting, we look at charging patterns. So for example, for an EV driver that has access to home and workplace charging, some common assumption would be that most of the energy comes from home and workplace, maybe 70% home, 10 or 15% workplace, 5% of the energy would come from fast charging on highways, and the rest 5 or 10% comes from destination charging at shopping malls or restaurants. So that's the 3 first steps of the fleet and charging modeling. And the last step is to allocate the charging to where EVs are actually charging, because an EV driver might live in location A, but go to work in location B. So you have to make sure that home charging is assigned to location A and workplace charging to location B. And that's the last step that is shown here. So that's a bit about the methodology. Now the fleet and charging modeling results are on the next slide. The table presents all the results for all the different EV fleets. Each line represents a charging setting. So for example, the first line, EV1, represents home charging, and you can see different assumptions for charging power, energy demand, and then the share of total EV fleet demand. One column to pay attention to is the 4th column, the smart charging column. You can see it's written yes or no, and it's related to the assumptions we made related to the manageability of the charging. So for example, EV4, you can see, EV4 or 5 public fast and highway ultra fast charging are non-manageable. So we assume that there wouldn't be smart charging at those locations because people come and they're not flexible. They come, they charge, they leave. That's an assumption. In some cases, highway fast or public fast charging can offer smart charging, but that's the assumption we made. So that's about it. That was quick about the fleet and charging modeling demand, because most of the interest is on the smart charging benefits. And before passing it on to my colleague Marin to walk through the next part, I will just remember all of you that if you have questions, you can write them in the Q&A chat, and we will be answering them either as we go or at the end during the Q&A session. So yeah, Marin, the floor is yours.
Thank you, Marie. So you can go next slide, please. Okay, so once we have defined the modeling of electric vehicles, we had to set up a strategy to evaluate the savings allowed by smart charging. So to this aim, we have defined different scenarios corresponding to different breakdown of charging modes. And from that, we expect to evaluate the benefits of smart charging by comparing the results for each of the scenarios. So we have defined 3 charging modes. Firstly, so the uncontrolled charge without any intelligence, the smart charging, which I will define more in the next slide, and bidirectional charging, so vehicle to grid, which is I think the the best we can have in terms of smart charging. And we have defined 3 scenarios. So from the low flexibility scenarios with only 30% of the vehicles being smart, the high flexibility scenario with 90% of the vehicles being smart, and the last one, the vehicle to grid scenarios with also 90% of the vehicles being smart, but 10% of them are able to reinject energy in the grid when prices are high. Can go next slide. Okay, so each of the charging modes are associated with specific load profiles, and to define the smart charging profiles, we had to design a price signal, and we made it with 2 components. So you can see in the chart here. So in blue you have the time of use components, which represents the network fees. So the prices of this component are high when we have peaks, so on the morning and on the evening. And the second component, the orange one, is more dynamic component reflecting wholesale prices. So therefore favoring areas with high renewable production and low production price. Okay, can go next slide. So from these assumptions on flexibility scenarios and the tariff, we can build load curves based on arrival and departure curves for each of the fleets. So we had 2 types of load curves per fleet. The first one is the in-control load curve. So they are directly derived from the arrival and departure curves. Basically, as soon as a vehicle plugs in, it starts charging. And the second type of profile is the smart profile. So they are obtained thanks to an optimization calculations, and that's minimizing the cost of charging given the constraints of arrival and departure. So at the end, we aggregate load curves for each of the fleets according to the percentage I presented in the different flexibility scenarios. Okay, we can go next slide. So in terms of grid modeling now, so we use a model developed by Artelys. So we modeled the medium voltage grid, so from high voltage to medium voltage stations through the medium voltage lines to the medium voltage low voltage substations. And from that, we, as Mary said, we distribute the load of each fleet according to relevant geographical keys. So for example, charging at work is distributed according to the number of employees in each zone. And for each of the EV fleet, we had the specific key. And from that, we carried out load flow simulations that allows us to analyze 2 main indicators. So the first one is the apparent load at substations and lines, and the second one is voltage drops at substations. So you can see on the map here, the apparent load per substations in the low flexibility scenario that we evaluate at peak consumptions, and we aggregate the results at 1 square meter, sorry, mesh, which facilitate the reading. Okay, we can go next slide. So in order to be able to draw conclusions on the need for grid reinforcement, we had to estimate an initial sizing of the infrastructure, given that there is no publicly available information for that. So to do this, we used the grid modeling for the reference year, so 2022, and we assigned nominal capacities to all the lines and all the substations according to the calculated load we have for this reference year, and also according to a catalog of available line capacities and transformer capacities. So you can see on the map here for transformers, all the dots represents all the substations in the area, and the color depends on the nominal capacity we have assigned based on the methodology I just presented. And we did the same thing for lines, and in addition for lines, we assumed the capacity margin of 50%. to represent the way that it's actually designed. Okay, you can go next slide, please. So from that, we had to estimate the need for reinforcements. So we assume that reinforcement is required as soon that the calculated loads in 2040 is overpass the nominal capacity. So you can see here on the map, all the dots represent the substations that, based on our methodology, require a reinforcement. So where the calculated load exceeds the nominal capacity we have assigned, as I presented previously. So all the dots are all the substations that need reinforcement in the low flexibility scenarios. And in green, you can see the substations for which we observed a need for reinforcement in the low flexibility scenario, but not in the high flexibility scenario. So we can see already that to have a more smart vehicles can allow us to avoid some reinforcement. So we did this for substations, but also for lines. And for lines, when we observe that the load exceeds the nominal power, we consider the length of lines to change in order to quantify the quantity of infrastructure to reinforce. Okay, and you can go next slide, the last one for me. Thank you. So in order to obtain indicators in terms of money that could be saved from these avoided reinforcements, we have associated this to simplified cost models based on each other. So for substations, we assume a model with a fixed part and a variable part proportional to the overload. And this allows to capture a threshold effect when the load exceeds the capacity, but also to capture the magnitude of this reinforcement. And for the lines, we have adopted a linear model. So the cost is proportional to the length of lines to reinforce, given that we observe that the cost depends less on the capacity to reinforce than to the length of lines to reinforce. And so from this methodology, we could have indicators in terms of money, of quantity of infrastructure. And I think that Julia will present it in the next slides. Thank you.
Thank you, Marin. I'm now gonna take us over to the results that we found based on the methods that Marin just presented. So, next slide, please. First, what we could clearly see is that optimized EV charging helps to reduce peak load in the studied area. Without smart charging in place, with low flexibility, without smart charging in place, peak load in Essonne is about 1,134 megawatt in 2022, which is our baseline year, and that will increase by about 1/3 in 2040 without much of optimization. That's what you can see in the red bar. And now from there, these are the results for the sort of subsequent steps of optimization. With optimizing charging, based on prices, we can reduce peak, and that is shown in the blue bar. In the high flex scenario, the peak load increases or decrease compared to the red bar, and the peak load overall increased less than compared to the base load scenario. The reduction or the comparison between high flex and low flex is about a 6% reduction. When we look further into bidirectional charging, this can further reduce system peaks and therefore reduce system costs. In our modeling, we could see that we could reduce peak by a further 3%, peak load now being at only about 1,300 megawatts. So this illustrates the high potential, especially of bidirectional charging, to reduce network peaks. Because remember, in this scenario, we looked at a relatively small share of only 10% of all controllable EVs being able to charge bidirectionally. From these overall results, I now want to take you to the more detailed results, looking into what contribution each EV fleet can make to reduce the peak load, as we've seen here. So on the next slide, I'm going to start with the, let's say, most best known or most classic use case, residential EV charging. This is looking into a residential area within the Essonne area we studied to highlight those results. If you look at this graphic, we will always compare the low flexibility scenario on the left hand to the high flexibility scenario on the right hand. And what you can see here, if you look at the red portion on the left hand graph, is that there is a peak in the load curve at around 6 to 7 p.m., which is typically when residential EV users would come home and are assumed to plug in if there's no optimization happening. After optimization, that's on the right-hand side, you can see that this peak completely disappeared, and that the charging of the residential EV fleet is much more spread out during all night hours, filling the sort of night valley that you could see in non-optimal charging. So this is an illustration of how residential charging or smart residential charging can reduce the load curve in a specific area. Now, let's look into the next use case, which is or the next result, which is an illustration of how smart workplace charging looks like. Again, we've zoomed here into a specific area within the Essonne area we studied, where you would have a lot of commercial or office buildings. So we could illustrate the impact of this shift on the load curve. So what you see here, again, on the left-hand side, the low flexibility scenario, you can see a very clear peak in the morning hours, which is typically when you'd assume EV drivers go to work and plug in their EV at an office parking, for example. That is the purple portion of the curve on the left-hand side. In the high flexibility scenario with smart charging applied, you can see that this peak again has been clearly reduced, and the charging of the EVs charged at workplaces is spread out within the entire office hours of about between 9 a.m. to 6 p.m. Now going to the next slide, where I want to illustrate the third sort of use case for smart charging we identified based on our analysis, which is smart depot charging. This is zooming in again into another cluster within Essonne, where we would have a lot of freight depots, logistics depots, and we could see the impact of smart charging of trucks parked at the depot on the local grid. Focus on the left-hand side graph again, this time on the light green portion of the load, which is representing trucks charged at the depot. You'll see here that in the non-optimized scenario on the left-hand side, there's much more charging happening in the early evening hours when these trucks return to the depot. And then there is, like in residential EV charging, a bit of a valley between midnight and and 5 or 6 a.m. After optimization on the right-hand side, you can see that the peak, the evening peak is reduced, and instead the charging has nicely spread out across all those night hours, really using the flexibility of those trucks parked at the depot during the entire night. I want to use this last slide, the results slide, to also illustrate another additional finding. Sorry, can you go one back, please? Back to smart depot charging. Also, please have a look at the dark blue portion on the left-hand side of the graph, which is a peak in the morning hours between 9 and 12. And that dark blue portion actually represents trucks charging at highway chargers. And this is a bit of a challenging use case for smart charging. As we know, trucks charging along highways have little flexibility windows, at least assuming that discharging is not helped by any battery storage or other optimization on site. So if that's not the case, discharging is not that flexible. And we could see, if you look at the right-hand side again, concentrating now on the dark blue portion, we can see that we also managed to reduce peak, that peak between 9 and 12 by a little bit. And how did that happen? Well, the portion of that truck charging along highways actually did not reduce as such, as it's not that flexible and can't really spread out over time. But because of smartly charging other EVs that are also charging in that area, most notably at workplaces, that's again the dark purple portion, now at the right-hand side, we could reduce the peak overall in the system that we're seeing at that particular time of the day. What does that mean? That means that smart charging is really a collective task. Other flexible EV fleets sort of helped out the trucks charging at the highway not to add to the system peak at that particular time, at that particular place. And it's nice to see the illustration of smart charging, because it conveys really, really important finding, and I'll get back to that in a second. It's that all different fleets and all different user groups of EVs really need to contribute to reducing peak load in the system by using their flexibility, whether it's a lot or not that much. And that's how we get to this overall peak reduction that we could find in this study. Right. I now want to sort of zoom out of the fleets and go to the next slide and discuss what all of that means now for saving costs on the system. All these peak reductions that we've just discussed translate into less need for grid reinforcements that we have estimated for this area, as Marin has shown, based on two main metrics: reinforcements of substation units and also of line kilometers. And I'm not going to go through all the details that are summarized in these graphics, but if you just look at the reductions that are possible in the high flex scenario compared to the low flex scenario in both graphs, the left one is substation units, the right one is line kilometers. You see that there are significant reductions already happening just by moving to more smart charging, and a lot more reductions if we factor in bidirectional charging. So overall, based on these results, a broad estimate is that smart EV charging can save up to 25% of network costs annually. Right, I think I'll leave it here with detailed results. A lot more, of course, is explained in our study, and you've received the link in the chat already. I'll now move on to wrap up with some conclusions and, of course, recommendations from our insights. Next slide, please. The results and the finding clearly illustrated that using EV flexibility can reduce peaks in the system and allows savings in network reinforcement costs. in that area. It also showed that smart EV charging is a collective task in the sense that different use cases contribute to make these savings available. Results showed that focusing on smart residential, smart workplace, and smart depot charging seemed the obvious place to start because that's where most flexibility can be harvested. And that is perhaps a reflection that is interesting for policymakers and planners that are writing strategies for electrification. We'll discuss policy recommendations in a second, but we can also already see that one of the key ingredients to make sure that those savings can be made, that smart charging actually happens, is cost-reflective pricing of using the networks. If users don't actually have an incentive to move their charging in the first place because it is cheaper, then we're not likely to see optimization happening. Now, this gets us to the recommendations that I'll quickly discuss before wrapping up. I think the study shows that it is really important to ensure smart residential, smart workplace charging, and also smart depot charging for trucks are the default mode of charging EVs, and that this way create maximum benefits in the system that can be harvested. Smart charging should simply be default in all use cases. To make that happen, we need to much more broadly introduce cost-reflective pricing of power networks, for example, through time of use varying network pricing, time varying pricing, sorry. We have presented one way to design such a tariff that we assume for this study, but there are many other designs possible. The essence is always to convey enough of an incentive for users to shift their charging and use the flexibility they have. It's also key to require transparency on network use from distribution grid operators. These are key players, of course, to make smart charging happen. We need to know what's happening on the grids to be able to offer optimization services, for example, through aggregators, but this is also highly important for developers of charging infrastructure, of course, as well as it is for depot owners, or think of any other use case. On the energy side, it's also key, on the energy policy side, it's also key to create the frameworks that allow EVs to participate as flexibility resource in energy markets and being remunerated for that. This, again, involves smart tariffs, but it also involves thresholds for recognizing, for allowing EVs to participate in energy markets as demand-side resources. And allowing them to aggregate and play a more important role equal to other resources. And last but not least, and this is a recommendation that I think is equally important for transport and energy stakeholders, it is really, really key to facilitate joint planning by the transport and the energy sector to make smart charging happen. And this includes, for example, accurate forecasting of the demand for charging coming from projected EVs in a certain area. It also includes rightly sizing or balancing the build-out of charging infrastructure, public infrastructure versus semi-private or private. As well as rightly sizing the planning of distribution system, local distribution systems or system upgrades. So there's a lot more that can be discussed on these policy recommendations, and I'm happy to do that. I'll wrap up now. Yeah.
I think that either the screen is frozen, but there was a recommendation slide maybe just after, or maybe the screen is frozen, I don't know. Okay, maybe just a sec for people to, so that's what Julia just went through, recommendations. Just a sec for people to read through it and maybe go to the findings after.
I should have said next slide, please. I apologize. All right. All these recommendations are detailed as well in our report. Now, leaving you with the key findings on this slide. That's perfect. Thank you. So really, smart charging is absolutely key to prepare electrification of transport in a grid-friendly system-friendly way in Europe and in all global regions. And this includes anticipating demand and increasing transparency, putting cost-reflective pricing in place, and collaboration between transport and energy stakeholders. Here's our study. Feel free to download it and get back to us with any questions that we haven't answered now or in the discussions or later on. And with that, I'll hand it back to Marie.
Yeah, thank you. So thank you very much, Julia, for the presentation you just made, and thank you also, Marin, for the presentation earlier. So now we will move on to the Q&A part of the webinar. Marin, you can also turn on your camera if you want, and then we'll go through the different questions. So don't hesitate to keep posting in the chat, and I'll go in order. I see that many questions have already been answered. I might go back to some of them to add some clarification, but first I'll go in order of the questions that haven't been answered yet. So there was one question about considering additional demand of EVs on cold temperature. So I'll add one thing on this, and then Marin maybe can complement. We used an average kilometer driven and energy efficiency of EVs, so not specifically conservative, but I do think that the load, when Julia was showing some load impact for smart charging on depot, workplace, and residential, this was for the worst case. So Marin did the grid modeling, but I think it was a day in January where the French system is the most loaded. Marin, maybe you can comment on this.
Yeah, exactly. So when we evaluate the load, so we aggregate all the loads from all the consuming sectors, so EVs, but also residential, industry, and tertiary buildings. So, and yes, the peak load is classically in January. I forgotten the day exactly, but yes.
Yeah, perfect. I hope that answers this question. And then there was a question about the correlation with the Euroelectric and EY report. So nope, there is no correlation between our report and EY report. I think it just shows that smart charging, bidirectional charging are very big topics nowadays. More and more organizations are looking into it, and policymakers, industry, etc. So it's another great report. I recommend you to read it, but there is no parallel between these two studies. And then there was a question from Tim. Does smart charging scenario consider only charging at charging station owned by a company or also public stations? So that was shown on one, if I understand correctly, your question, you're referring to where does smart charging happen? So which chargers are deemed manageable? So which chargers offer smart charging? So for light duty vehicles, we assume that home, workplace, and public normal chargers would offer smart charging possibilities because there would be enough flexible time for people to charge. And for heavy duty vehicles, that would be depot charging, and the other, so public fast and highway ultra fast chargers, would not be manageable. So we also have some public smart charging, but public normal and not public fast smart charging. And I hope that answers your question. If not, if I missed the point, don't hesitate to add your question again in the chat. Then there was a question from Art on price elasticity on participation. Maybe I can let Julia or Marin. So I don't think it was considered in this analysis, but maybe they have done some other studies on customer participation depending on pricing. I don't know if one of you want to answer this one.
Yes.
If not, that's okay.
Yeah, I can give maybe an answer. So we designed the tariff based on I said the time of use component, and the other component was the wholesale price from 2022. So it was actual wholesale price, and so we used a calculation that's it's an optimization calculations which try to capture the behavior of a user, but we didn't made more research in this in price elasticity, in how we could achieve this in reality. But okay, yes.
Yeah, thank you, Marin. Maybe Julia.
Yes, sorry. And now just to complement, so we have indeed assumed that that consumers are 100% responsive to the price signal they get. Now, behavioral research, of course, can go into a lot more detail and sort of correct perhaps one of these this assumption. But for the analysis to show the effect, we have sort of simplified that and assumed the same responsiveness across all consumers and all groups for this study. That's something that, you know, if you were to go more into tariff design to further optimize the benefits or to further reduce costs of optimizing charging, that is the type of assumptions that you would detail out more. At some point, as you may remember from the research design slide, this is quite a complex study, and we had to build a number of sort of sub research pieces into this. It is not a study on tariff design. So the study is not to find out what is the best possible tariff to get to optimized result. The idea was to show to quantify those benefits in the first place. And one of the further research areas is actually to refine those assumptions on the tariff side.
Thank you, Julia. Then there was a question about effectively communicating results. That's a great question. I mean, that was also one of the goals of this project, to analyze but not stop at the end of the research, but keep communicating the potential benefits. I'll give my personal answer, and then I'll let the other speakers also answer. For me, there is push and pull mechanism, so kind of regulatory aspect mandating it. Some countries have started doing this. For example, in the UK, there is the smart charge point regulation that has some more specificity that goes beyond what is already in AFIR, so the alternative fuel infrastructure regulation, that mandates the smartness of the charger, but doesn't go beyond, whereas the UK regulation goes beyond with a predefined smart cycle that the user has to overrun. So there is more those kind of push, and then there is more kind of incentive. So the price incentive is a great one to push people to use more smart charging, and then just making people, I think, more aware through events like this. But maybe, Julia, I know that you do quite a lot also on communication after, so maybe you want to compliment on this.
Yeah, I think the moment in time is perfect to talk about smart charging. We're seeing more and more studies done. I think this is a really important area in which we need to produce more knowledge. And there's two types of savings that we can describe. We can describe savings that are made in the system and on the grid, and that's where I think our study hopefully created some more knowledge. And there's another area in which we can create or show that more savings can be created, and that is from taking the user perspective, whether it's individual users or fleet users. And I think both are needed to make basically everyone more aware of the savings that can be made. So communicating and sharing these numbers based on examples from specific markets, you know, even localities, cities, etc., is super important to illustrate how much can be saved. I think that's my number one answer. I think the time is also perfect because on European level, we're seeing a couple of policy initiatives that will require smart charging to be default in the end across the continent. I'm thinking of the Affordable Energy prices action plan that has just been released a couple of weeks ago. The European Union is making a big effort to keep energy or electricity bills affordable, and smart charging is part of the answer, where we can optimize, where we're saving costs in the system, which in the end brings down costs for everyone, including costs on the energy bills. And I think that's a really important link that we can stress. We're going to see other initiatives by the end of the year, including grid package, for example, that will you know, focus on energy efficiency and integrating more renewables. So it's how to make you know, users participate in the energy transition and spelling out these benefits that would really help to make the case for optimizations such as smart EV charging.
Yeah, thank you. Yeah, lots of exciting movement on the policy scene this year. Shows great momentum on this topic. Then there was a question. I see, Andreas, that you're starting to answer it. Andreas is also a co-author of the study, was not a speaker, but a co-author. So I don't know if you want to talk. I think you just answered it, but if you want to give your answer live about the influence of smart charging on the number of smart chargers. So basically it doesn't really have an influence would be my answer. But maybe, Andreas, you want to answer this?
Thanks a lot, Marie. I try to do, but I can't switch on my camera. Sorry for that. It could be even likely that we need more chargers if we extend the time of the EVs occupying a charger with that. But that is uncertain, and we don't know really what the percentage is at all, what we need for charging stations, or if it is behind the meter, or if it is fast charging. So there's a lot of uncertainty in that. And I would say it depends really in the composition of the entire system.
Yeah, thank you, Andreas. I would say the same. At ICC, we haven't done a study on this, but indeed, smart charging could increase the potential hours during which the chargers are plugged in. But there is no clear estimate on this. And then there was a question from Vitold. I see, Julia, that you're starting to answer it. It's in regard the impact of the AFIR regulation, alternative fuel infrastructure regulation that I mentioned. It's this EU regulation on charging infrastructure. And did it have an impact on our work and calculation? I can maybe first answer from ICCT side. So AFIR does have an impact because that's what I mentioned when I was speaking about fleet modeling, fleet and charging modeling. Our models take into account adopted policies, and AFIR is an adopted policies. A big other influential adopted policy is the CO2 standard that influences the number of EVs, light and heavy-duty vehicle that we will have on the road. And AFIR also influences this more in the sense of the targets for the number of chargers along highways, so the distance between the different chargers, that influences our result. The kilowatt capacity, that doesn't influence it that much because our modeling estimates slightly higher charging infrastructure needs than what is recommended, what is required by AFIR, but the highway ones did influence it. And I don't know if anyone want to add something else to this.
Yeah, perhaps a quick addition, bringing in AFIR is a good keyword, of course, when you talk about smart charging. I think another important point in this regulation, aside from setting targets on density and capacity, is that it requires all new charging points to be smart charging capable. And that is a good sort of minimum requirement at the charging infrastructure. However, we need to also improve energy market regulation, the framework around it, so to speak, to make sure that smart charging is actually rewarded. And this is why I mentioned in our set of recommendations, smart cost-reflective tariffs, lowering thresholds for demand-side resource participation, etc. So both go together. AFIR is sort of creating the public charging network backbone based on which a market for smart charging services now needs to develop.
Apologies, I forgot to unmute myself. Never mind. I don't see any new question, but I'll go back to the answered questions because I think we could add some clarification to some of them. And in the meantime, don't hesitate if you have any additional question. You can also reach out to us afterwards if you want some more clarification. There was one question I think we could clarify about if we consider the GHG saving potential from this. Julia, I mean, I'm more aware of the European studies since we have done studies in other markets. I don't know, have we considered this in one of the other studies? Julia or Andreas? I guess the short answer is no, we haven't.
Right. Julia should answer or might answer, but she can't do it at the moment, as it looks like. Sorry for that interruption.
Sorry. Yes. So in the EU study, excuse me. In the EU study, indeed, we focused on the economic benefits only, since in regions as Europe, the sort of grid constraints and how to overcome them is really the biggest bottleneck for smart charging. The narrative looks slightly different if you look, for example, into India and China. I think China is the most telling example. In our China study, we focused on a province that has very high EV targets, both for passenger markets and trucks, and we could show that by doing smart charging, by using EVs as flexible grid resources, we could not only achieve economic savings, but we could also reduce the share of coal power used to charge these vehicles, hence integrate more renewables and sort of contribute indirectly to or to create a market incentive for more renewable power built in that region. More of these results will be published in our global summary, but our China study is already available in an English summary, and I'm happy to post it in the chat. A similar, I think, story holds true for India, where the EV market is, of course, still nascent, in particular in the truck segment, but with very high growth projections. And there as well, there's a clear case to be made for electrifying transport, which would also lead to bringing in more solar energy use. So in our China study, we looked at how we can optimize the charging of electric trucks at highway stations during the day, according to or incentivized by solar rebates, so which make solar electricity, which is plentiful, available, cheaper, and sort of ensure it's more likely to be used. So in that region, we made the case for solar smart charging, which seemed to be, let's say, the #1 driver for optimization. Whereas in the US and in the Europe study, the driver for optimization were grid constraints and matching this with the flexibility windows we had in different fleets.
Yeah, thank you, Julia. So great adaptation of all the studies in the local contexts. Maybe also adding into one question, and I think then it will be time to wrap up. There was one question about the 10% bidirectional charging. So there was one comment about this fact that this is a conservative estimate. Indeed, this is quite a conservative estimate. This is just the first kind of small sensitivity analysis to do a first try at assessing the potential of bidirectional charging. This does require way more analysis. This study focused more on smart kind of unidirectional charging and added this at the end. So 10% is conservative, but we already see that with just 10% bidirectional charging, there is a decrease of 9% in peak load. So it's just to show that there is potential and there needs to be more research on this. And maybe Marin, you can elaborate on what does 10% bidirectional mean, because I've had this question quite often. I agree that that's not straightforward. So Marin, maybe you can elaborate a bit on this.
Yeah, so we defined the percentage. It represents the amount of energy associated with the charging mode, but it's possible to interpret this as the number of vehicles as soon as you assume that each vehicle consumes the same, not depending on the charging mode, neither on the EV fleet. So it's precisely it's the amount of energy, but it can be interpreted as the share of EVs which are concerned.
Okay. Yeah, maybe it can be interpreted, or correct me if I'm wrong, but kind of 10% of the energy kind of comes directly from another EV's battery. It's 10% of the energy charge that would come from this bidirectionality.
Yeah, exactly. Yeah.
Okay. I see that most of the other questions have been answered. I won't go through all of them. I won't have time to read through all of them, but thank you to the speakers and to Andreas for answering the other question. So, okay, there is another question that arrived. Sorry, so maybe we can answer this one and then I'll wrap up. Andreas, you're already typing, so if you want to take that related to CapEx and OpEx, I can give you the floor.
No, we did not look into this. It is quite complex at the end because we would have to define a baseline in the first, and that is already a huge guessing. How much of investments of CapEx do we need compared to, and then to OpEx? That would be an entire study by itself.
So maybe ideas, if people want to take that on as a study, there are many ideas, many new research that can be done. And then on this nice note, I'll close it here. So I see some additional questions, but I think we'll have to close the webinar, and we can definitely get back to you, or you can reach out to us. If there is no emails, you can go on the different websites, and you'll have some contact to reach out to our communication team, and they will forward the questions to the right people. But thank you everyone for joining today's webinar. Again, reach out to us if you have any questions. And last note, you can follow us on our social media channels, subscribe to the newsletter to have more update on such projects. So thank you everyone, and hope to see you soon.